Now, I want to address specifically the minimal testing of the F1 engines and some of the comments that have been made from the NASA proponents that the reason for the minimal testing is because of the enormous cost that would have been involved. Now, there is some truth to what they're saying. But somehow they're justifying safety for money. They're justifying safety for money, which I have never heard done before in any other industry. So that's a very interesting admission from the NASA proponents. Now, what they're also saying is that these are single-use engines. And what they mean by that is when you launch a Saturn V rocket, you've destroyed the F1 engines. It's a one-time use, so they can't be used again. So their justification for the minimal testing is that they would have had to purchase new engines. And that's true. But what they need to do is that they need to keep doing that. It doesn't matter what the cost involved here is. We're talking about the safety of astronauts. You certainly wouldn't get away with that in aviation. Not that that actually happens, because those engines are actually, are reusable, as everyone knows. However, the point is that yes, NASA would have had to pay the cost for those F1 engines each time they wanted to launch a Saturn V. But we're looking for consistency in terms of data, and that is the benefit of doing testing of the F1 engines in the Saturn V. And that's what I'm talking about in terms of finding at least some comparable testing to the static testing that was done. Now, the static testing that was done amounted to about 70 hours, which is, fairly substantial. And I can understand the reasoning behind not being able to match that 70 hours in terms of testing the F1 engines in actual flight conditions. That does make a lot of sense. But there is one interesting aspect to that, and I'd like to read a quote here. It's from thespacereview.com, and it's by Dwayne A. David. And this is what he says, quote, "The 5-engine cluster used on the Saturn V was fired at the Mississippi and Alabama test facility 34 times with full 18 full duration tests for a total of 15,534 seconds of engine experience." That part of the quote I want to read again here. With 18 full duration tests for a total of 15,534 seconds of engine experience. Now, what he's talking about there is that they did a cluster of 5 F1 engine tests, which is basically simulating what you would actually have in the Saturn V rocket in the first stage, because each rocket had 5 F1 engines. And they did 18 full duration tests, which is just over 2 minutes each. So we're looking at about 36, 37 minutes of actual testing there. That is the number that NASA could have matched, and it didn't. As we know, there was only 2 unmanned launches of the Saturn V for a total of 4 minutes combined for the use of the F1 engines before they sent up the first manned mission. As we know, there was only 2 unmanned launches of the Saturn V for a total of 4 minutes combined for the use of the F1 engines before they sent up the first manned mission. Now, here's what's very interesting about that. The H1 engines. The H1 engines were basically the precursor to the F1 engines. It's basically the same engine, only a lot smaller and less powerful, had the same regenerative cooling system. Now, what's interesting about the H1 engines, which was used in the Saturn rocket and the Saturn V, is that it had numerous testing, static testing, but it also had a comparable amount of testing in actual flight conditions. In fact, all you have to do is refer to any book on the Apollo missions. Here's one here, the Saturn V by Alan Lowry, and turn to listings of all H1 engines right here, page after page after page. And what these pages represent is not only the testing, the static testing, but how many times that engine was launched. So I have a question for the proponents, and I'd like you to blog your answer, post your comments on this video. How many launches did the H1 engine have before they put the first crew on board, which was Apollo 7, because it used the Saturn V? I want you to post your comments, and I want you to justify why you're saying what you're saying about the H1 engines, because you know what? Here's a hint. They did a lot more testing of the H1 engines in practical conditions of flight than they did with the F1 engines. So I'm interested to see your comments on that. So anyway, that's all for now, and I'll see you in the next video. Bye for now.
When I started researching this, there was two aspects of the Apollo missions that really stood out for me. The first one was the Apollo guidance computer and its navigation system. And the second was the F1 engines. The F1 engines were the most powerful engines ever built. and were only used during the Apollo moon missions. They were never used after that. That whole program was ended after the Apollo mission, the last Apollo mission in 1972. These engines were developed specifically to lift the enormous amount of weight of the Apollo hardware into low Earth orbit. They were needed to get the rocket off the launch pad. Without the F1 engines, that could not have happened. There is no way that they could have lifted that hardware off the launch pad. And if you can't do that, ergo, you have no Apollo moon missions. So they were having some problems with the F1 engines. The main problem they were having is a thing called the combustion instability. What that really means is, so you have the engine, and then you have the fuel injection system. Then you have the combustion chamber, and then you have the throat, and then of course you have the nozzle. So what was happening with the combustion chamber, the F1 engines, is the temperatures were reaching so high, up to 6,000 degrees Fahrenheit, that the cooling system was having a problem maintaining lower temperatures, because if you could not lower those temperatures and keep them constant, just the enormous amount of heat produced in the combustion chamber from the explosion of the propellants was going to distort and then eventually lead to an explosion and of course loss of the engine. And if that engine was of course used on a Saturn V, then you have the loss of the whole mission. It was when they got to the second version of the H1 engine that they realized that they were having the same problems with the F1 engine was having, and that is they used the same system. It was the same regenerative cooling system, the small tubes that were placed outside of the nozzle and the combustion chamber to absorb the thermal energy of the high temperatures, which could reach up to 6,000 degrees Fahrenheit. Interestingly enough, the H1 engine was using the same material as the F1 engines for its cooling system, and that was the nickel alloy that I had just mentioned. So what did they do? They solved the problem. And how did they solve it? They solved it with eliminating the use of the material that they were using for their cooling system in the H1 engine, and went back to using stainless steel instead. And then the engine worked perfectly. However, that wasn't done with the F1 engines. They had to stay with the original material they were using, which was constantly breaking down due to erosion. And that's where it sort of rears its ugly head. But it was the second launch, Apollo 6, where they had serious problems with the F1 engines. The Apollo 6 F1 engines were firing unevenly because of the combustion instability. And because they were firing unevenly, they were sending a resonance through the longitudinal axis of the rocket, which was causing a thing called pogo. So you had a pogo effect.
Today I'm going to be talking specifically about Apollos 4, 6, 8, 9, 10, and 11. Now, Apollo 4 was the first test of an all-up Saturn V. So that's an all-up test. So that included all the parts that had never been tested together before was done with Apollo 4. Now, this was an all-manned launch. This mission apparently went perfectly, according to NASA. The second unmanned test of the Saturn V was with Apollo 6. This mission was plagued with problems that NASA does admit to. Now, NASA says the problem with Apollo 6 was pogo oscillations. And because of the pogo oscillations, the engines in the second stage, the J2 engines, were disrupted. So they had multiple failures. I believe they had 2 failures. Actually, 1 failure, and then the computer for some reason shut down the second engine. And NASA said this was caused by disruption in the fuel lines brought on by pogo oscillations. Now, what pogo oscillations is instability along the longitudinal axis of the Saturn V. The problem that NASA does admit to, actually, that they had constant problems with the F1 engines, is the area of the combustion chamber. This, NASA says, caused the problems. But when you look at this a little further, you notice that NASA never says anything about the F1 engines. It never says that they were disrupted, by any fuel lines breaking, but interesting enough, it did affect the second stage engines and the third stage engine. So when you look further at this, you find out that actually it most likely was the F1 engines. And in fact, it was the F1 engines, not most likely. It actually was a problem with the F1 engines. Now, to explain, the F1 engines are needed for an Apollo moon landing. And the reason being is the F1 engines were supposed to be the most powerful engine, rocket engine, ever produced. Each engine would produce a thrust of 1.5 million pounds. There were 5 of these engines in the first stage of the Saturn V for a total of 7.5 million pounds. Without 7.5 million pounds, you cannot launch an Apollo payload into low Earth orbit for an eventual trip to the moon. So therefore you have no Apollo landings. If the F1 engine is not working perfectly, you have no Apollo moon landings. Now, the problem that NASA does admit to actually, that they had constant problems with the F1 engines, is the area of the combustion chamber. NASA says that there was instability in the combustion chamber. Now, just to briefly explain a description of what I'm talking about here, when you look at a rocket, we all see the nozzle of the rocket engine on the bottom. On top of the nozzle is an area called the throat. On top of that is the combustion chamber. Now, and of course, on top of the combustion chamber, you have the rest of the engine that mixes the propellant and then sends it through to the combustion chamber for a controlled explosion. That controlled explosion is pushed to the throat and out of the nozzle, which propels the rocket. So NASA had to find a way, though, to cool the temperatures of the combustion chamber, which could reach up to 6,000 degrees Fahrenheit. So they came out with a method called the regenerative cooling system. This was used in liquid-fueled rockets, which the F1 engine was. Now what that is hundreds of small tubes that run outside of the combustion chamber, the throat area, and partway down the nozzle. And propellant would be pushed through these hundreds of thin, very thin tubes, and the propellant would absorb the thermal energy produced by the controlled explosion within the combustion chamber. And then that propellant would be directed into the combustion chamber, which is supposed to have made for a more fuel efficient or more efficient engine. However, there's where the instability is. The tubes were breaking down. And because they were breaking down, they were not absorbing enough thermal energy to keep those temperatures down. So it was creating instability within the combustion chamber. So in order to overcome that, NASA had to find a way. In other words, the only way they could do it was to use the F1 engines at lesser thrust. So if they were using less thrust, they weren't producing the power necessary, which defeats the whole purpose of using the F1 engines in the first place. This is apparent when you analyze Apollo 6. It was burning kerosene, which is very interesting, because the F1 engines were the only engines in the Saturn V rocket that actually used kerosene, along with liquid oxygen. Now, NASA says that they solved all these problems in just 7 months leading up to the next launch of a Saturn V, Apollo 8. Now here's where it gets interesting. Apollo 8 was the third launch of the Saturn V, but it was also the first manned mission of a Saturn V. So they sent the first manned mission of a Saturn V with only 2 all-manned tests of the Saturn V and its F1 engines. That is a total of 19 hours for the Saturn V rocket and a total of 4 minutes for the F1 engines. Look to aviation. You try to do something like that in aviation, you would be laughed out of the room. In aviation, even with today's sophisticated technology, and by comparison to 50 years ago, and software techniques that are used to design these aircraft, they still do hundreds of hours of testing on the engines of these aircraft and on the airframes of these aircraft before these planes are certified for commercial use. But not so with NASA. NASA said that with only 2 unmanned launches of the Saturn V, for a total of 19 hours and a total of 4 minutes with the F1 engines, in which one of these unmanned launches, Apollo 6, was plagued with problems, that they solved all those problems in just 7 months without any further testing in the actual conditions of flight to send the first manned mission on Apollo 8. And NASA claims that it worked perfectly. Now, I might add that Apollo 8 was not only the first manned mission of the Saturn V, it was the first manned mission to leave low Earth orbit and circumnavigate the moon, according to NASA. Now, you can factor in Apollos 9 and 10 leading up to Apollo 11 and say, well, there was 2 more rocket launches. But when you total up the total time of these F1 engines, they had about 10 minutes of flight testing total before Apollo 11. No way. Absolutely no way. And this is, for me, one of the biggest indicators that these missions were faked. You have a total, up to Apollo 11, you have a total of the F1 engines with 10 minutes of flight in actual conditions. Unbelievable. There's just no way. And there's no way they could have solved the problems with the Apollo 6 in just 7 months leading up to Apollo 8, let alone Apollo 11.